So modern atomic theory. Modern atomic theory is this idea that all matter is composed of atoms. And it grew out of observations and laws. The law of conservation of mass, that you can't create or destroy mass. The law of definite proportions, which we haven't talked about yet, and the law of multiple proportions. And those two laws may seem to contradict each other, but they actually don't. So conservation of mass, in a chemical reaction, matter is neither created nor destroyed. So this was come up with by Antoine Lavoisier, 1789, burning things in closed containers, right? When a chemical reaction occurs, not nuclear, a chemical reaction, the total mass of the substances involved doesn't change. It's consistent with atomic theory. Atomic theory explains this as the particles, the atoms, are just being rearranged. They're not being created or destroyed because the individual particles are indestructible. Okay, so that's why the mass can't change, because the particles are all the same. You're just putting them together in different ways, like Lego bricks. Here we have an illustration of a chemical reaction. Here we've got sodium metal reacting with chlorine gas. So here's a representation of sodium, and here's a representation of chlorine gas, little molecules. When these two things react and combine to form sodium chloride, the little atoms here, the green and the purple spheres, are still there. But instead of being separated and arranged like this, now they're put together in this pretty pattern, right? We see that the mass of sodium plus the mass of the chlorine that react here, a total mass of 19.6 grams, is represented in the total mass of the substance formed. Any questions? So the law of definite proportions, 1797, a French chemist, Proust made the observations on the composition of compounds. And he summarized those observations. This is a law. He says, I observe that this is what happens, not explaining why. That all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So, as an example, if we take 18 grams of water and we decompose it into hydrogen and oxygen, we're going to get 16 grams of oxygen and 2 grams of hydrogen. The mass ratio, oxygen to hydrogen, is 16 to 2 in that particular example. That's a ratio of 8 or 8 to 1. And what he observed is no matter what size sample, no matter where the water came from, when you decompose it and look at the mass ratio of oxygen to hydrogen, you always come up with the same ratio. Any questions about that? So there are some questions that may come up in homework worksheets or even on an exam that deal with this law of definite proportions. And my experience is that students, because you have all had a chemistry class before, students tend to go beyond what we've already learned and make this way too difficult. Okay? So let's look at this one. 2 samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen. I'm just going to go ahead and write that down. So 17.2 grams of oxygen and 12.9 grams of carbon. So that's sample number 1, we'll call it, because it's the first one we came to. The other sample produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. Law of definite proportions says that the ratio of the masses in a compound is always the same. So here we have mass of oxygen and carbon for each of 2 samples. What we need to do is find the ratio and see if it's the same. I prefer ratios that are greater than 1, so I always take the larger number and divide it by the smaller. So if we look at the ratio of oxygen to carbon, Okay, we can write ratios like that, or we can look at them as fractions. Fractions are easier in this instance. So I'm just going to put the mass of oxygen on top and divide by the mass of carbon. Calculator, 17.2 divided by 12.9. So I get 1.33, that would be 3 significant figures, 3. That's the ratio, and it just keeps going on. For the other sample, we're going to do the same thing. We're going to take the mass of oxygen divided by the mass of carbon. So 10.5 divided by 7.88. 1.33, again, 3 significant figures, and then the next 2 digits are 2,4. Are those the same? Yes, they are. The number that shows on our calculator is not exactly the same, right? After this second decimal place here, it's a little bit different. But this is where understanding the limitations of measurement is important, because these measurements were only made to the nearest tenth of a gram. And so when we get this ratio, we can't assume that we know all these digits. We use the rules for significant figures, and those help us to predict that it's in this second decimal place that we have uncertainty. We do this ratio, and again, with the 3 significant figures, this is the uncertain digit. And so these are the same even to the uncertain digit. If these were slightly different in the uncertain digit, maybe this one was a 5 and that one was a 3, I would still say that they are the same because there is uncertainty there. Okay? Any questions? So law of definite proportions, you're just taking the mass of each element and finding the ratio. If it's the same compound, the ratio of the masses will be the same. It's definite. It's always the same. So that's definite proportions. The law of multiple proportions, this is talking about looking at 2 different compounds made from the same elements. So 1804, John Dalton published this law. When 2 elements, and we're going to call them A and B, form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. Now, that probably didn't make a whole lot of sense. Another way to look at this is when an atom of A combines with 1, 2, 3, or more atoms of B. So we could have 1 atom of A and 1 atom of B. Or we could have 1 atom of A and 2 atoms of B. Or 1 of A and 3 of B. It has to be a whole number ratio of atoms, because the atoms are the smallest part. It's like people. You look at a family and there could be 2 male and 2 female, or 1 male and 3 female, but you can't have 1 male and 2.5 females in a family, right? You have to have whole numbers. So when we look at the masses of B that would react with a particular amount of A, we're always going to get small whole number ratios. So let's look at this example. Carbon monoxide and carbon dioxide. 2 compounds made of the same 2 elements, carbon and oxygen. Carbon monoxide is a 1-to-1. 1 carbon atom, 1 oxygen. Carbon dioxide has 2 oxygens for every 1 carbon. So if we look at mass ratios, oxygen to carbon, in carbon dioxide, it's 2.67 to 1. That's the ratio, and so we can say that there's 2.61 grams of oxygen that reacts with each 1 gram of carbon. We're not talking about what the atoms weigh or anything yet. We're just taking the masses of the elements in this compound and doing ratios. In carbon monoxide, the mass ratio of oxygen to carbon is 1.33 to 1, meaning 1.33 grams of oxygen reacts with every 1 gram of carbon. Okay, so we came up with these ratios. And if we take the ratio of the ratios, right? I know, it's getting a little weird. We take this number and divide by that number, we're always going to get a whole number. We're getting a number 2. And that tells us that this one has twice as many oxygens in it as this one. This is the sort of stuff that they were discovering before we could look at numbers of atoms and individual masses of atoms.
So
yes?
you're always going to get a whole number considering it has the same like makeup, like carbon and oxygen?
Yeah, you can only compare different compounds made of the same elements,
Okay.
same combination of elements.
Okay. And that, so the law only applies to those?
Yes. Yeah. If there was something that had 3 carbons, I don't think there is any CO3, but if there were, then we'd find that the ratio of oxygen to carbon of this one, if we related it to this 1.33, we'd end up with a whole number of 3. And that's telling us that this has 3 oxygens, this one has 2, and this one has 1. You can't have anything in between. It always has to be a whole number because of the individual particles. So here's an example of a problem like that. Hydrogen and oxygen form both water and hydrogen peroxide. So the decomposition of a sample of water forms 0.125 grams of hydrogen for every 1 gram of oxygen. So let's write that down. So we've got water, and we're getting 0.125 grams of hydrogen for every 1 gram of oxygen, sorry. And the decomposition of a sample of hydrogen peroxide, gives 0.250 grams of hydrogen, for every 1 gram of oxygen. And it's asking us to show that these results are consistent with the law of multiple proportions. So we've already been given simplified ratios. It's 0.125 grams per 1 gram, 0.250 grams per 1 gram. So we want to take the ratio of these. And again, if you take the larger number and divide by the smaller, you'll get a whole number. So we're going to take the 0.250 and divide by 0.125, and that's going to give us a nice whole number too. Bless you. Now again, these are coming from actual measurements, and so if it comes out to be 1.99993, it's 2. Any questions? So law of multiple proportions, we're looking at the ratio of the ratios. So Dalton's atomic theory explains these laws: law of conservation of mass, definite proportions, and multiple proportions. And these are the principles or the parts of his theory. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that make them different from atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. Now, this is his original theory. Can anybody point out some things that are not quite true? Are atoms indestructible? No. You've heard of atom smashing? Atoms can be smashed and broken apart. So do we throw out the whole theory? No. We just modify it. They are indestructible in a chemical reaction. We just exclude nuclear stuff from this. What about this one? All atoms of a given element have the same mass. That's not quite true either. The idea of isotopes hadn't been discovered yet. But again, we don't necessarily throw out the whole theory. We just modify it when we learn new information. I will not ask you to just regurgitate Dalton's atomic theory. But understanding the concepts in it is very important.